Okay, so you guys should already have an introduction to entropy and spontaneous processes or reactions from the video you watched Monday night. But we're going to keep going with the notes. So you should already have some of this underlined. I'm going to pull out some important pieces as well. So when we're talking about spontaneous processes, and all of chapter 19 is about spontaneous processes, those are things that can proceed without any outside intervention. And there's a couple of factors that play into if a reaction is spontaneous or not. So we've already talked about enthalpy. So enthalpy has something to do with it. Also entropy, and then a combination of that will be Gibbs free energy, which is what we're heading to this week. So when we look at if a process is spontaneous or not, if it is spontaneous in one direction, it has to be non-spontaneous in another direction. So the eggs fall to the ground. You don't have to do anything to get them to fall. Gravity pulls them to the ground. But then to undo that would not be spontaneous. It would require a huge amount of effort for us to get those eggs back to how they used to be. If a reaction is spontaneous, that doesn't mean that it's always spontaneous. It could be at one temperature and not at another. So the temperature or the energy associated with the system is going to play into it as well. So if we're just like out in a classroom above 0 degrees Celsius, ice is going to melt. If it's in a freezer, ice is not going to melt. So it's a spontaneous process at one temperature, but not at another. And then below 0 degrees Celsius, the reverse process is spontaneous. So if I put water in the freezer, it's going to freeze. It's not going to melt. I'd have to do something to get it to melt. So when we're talking about if a process is spontaneous or not, it's also important to know the temperature that the process is occurring at. Spontaneous processes don't necessarily mean that they're not reversible. So in a reversible process, the system changes in such a way that it can be put back in its original states by exactly reversing the process. An irreversible process cannot be done by exactly reversing the change to the system, which means that the spontaneous processes are irreversible. So they require something to undo the process. You can't just flip the reaction around. Okay, so one of the other pieces that helps us decide if a process is spontaneous or not is the entropy. So entropy is given the capital letter S, which is here. And it's basically a measure of kind of the disorder of a system or the randomness of a system. So it's related to the motion of the molecules, which means that it could be related to the temperature, but it's also going to be related to the structure and if it's a solid, liquid, or gas. So when we talk about entropy, we're going to talk about it in two ways. We're going to look at a molecular scale. So we're going to make some predictions based off of the things that are in a reaction. And then we're also going to do some calculations and do the actual entropy of a system. Okay. So on a molecular level, molecules are constantly moving, and they have different types of movement. So the first one they have is translational, which is movement of the entire molecule from one place to another. So this is the movement that we usually think about, is that with gas molecules, they're zooming around. Vibrational is the periodic motion of atoms within a molecule. So they might be moving kind of up and down. They might be moving side to side, okay? Or they might be kind of doing both of those things, okay? The last one then is rotational, and rotation is like actually the molecule is spinning. So when we think about the movement of molecules, they're moving from place to place, but they're also kind of shaking their arms, like maybe you've got like maracas, and spinning in place. So it's like a little kid dancing, right? Moving their arms, spinning around, jumping all over the place. So each of those types of movements is going to affect the entropy. Because remember, entropy measures the randomness. So the more types of movements it has, the more random it can be. So he referred to kind of all these different movements, all the different ways that a molecule could be, as a microstate. So if we took just like a quick snapshot in time and we looked at a group of molecules, all the molecules would look slightly different because they're all going to be kind of at a different point in their movement. The number of microstates that you can have, the more you have, the more randomness there is, the higher entropy. So if we look at this example here, we've got a red ball and a blue ball. And there are only so many ways that those can be. They can both be in the left side, they can both be in the right side, or they can be split one on either side in these two ways. So there are 4 microstates, kind of 4 ways that those dots or those balls could be next to each other. When we look at those microstates, we give them the letter W, that's a capital W. And K is a constant value. And we would be able to calculate the entropy. We're not actually going to do this calculation because for anything past kind of a 2 or 3 element molecule, this becomes really challenging. What you want to get from this though is that the entropy increases with the number of microstates in the system. So the more possibilities of where molecules could be, the higher our entropy is going to be, which is going to lead us to kind of a couple of things that we know about a molecular entropy on a molecular scale. Because increasing microstates increases the entropy, if we increase the temperature, that's going to increase the entropy. If they're moving faster, moving around more, there's more microstates. It also is going to increase with the volume. If they have more room to move around, there's more places they can be, which will increase those number of microstates. It's also going to increase as the number of independently moving molecules increases. So in that last example, if we put a green ball in there also, that's going to really change the configurations. So the more independently moving molecules, so the more things you have, the more entropy you're going to have. And then also the complexity of the molecule. So if you're looking at a molecule like water that has 2 hydrogen and 1 oxygen versus methanol, which is a carbon, hydrogens, and oxygen, that's going to have a higher entropy. This one is a little bit harder to figure out kind of that complexity of the molecule, so we're not going to look at that as much. Okay. A couple other things that can affect the entropy is the state of matter. So gases move a lot more and they're a lot freer to move. Liquids, they've got that flowing motion, which is going to be less random. And then solids are actually packed into a specific structure. And so they are going to have the lowest amount of entropy. Solutions, so when we take something, we dissolve it in water. So let's say we've got NaCl as solid, we put it in water, and it breaks apart into the Na ion and the Cl minus ion. Even though we're working with Na and Cl, we are going to be increasing our entropy. So we're going from one solid to 2 things dissolved in water. So this side has the greater entropy. There's more free moving things in that solution versus when they were in the solid form of sodium chloride. Okay, so we're going to make some predictions. So these are the things we need to remember. The entropy tends to increase when gases are formed from liquids or solids. So we're going from those liquids and solids, which have less motion, to those crazy gases. Liquids or solution, when liquids or solutions are formed from solids. So again, when we go out of that solid form to form a liquid or to dissolve. It might also increase if the number of gas molecules increases. So if we go from having like 3 moles of gas in the reactants to only 2 moles of gas in the products. The number of gas molecules increases, so this would maybe be a 4. So maybe we go from 3 moles of gas to 4 moles of gas. That would be an increase in entropy. And then also that goes with the number of moles in general. So if we start with 2 moles of a liquid and we end with 3 moles of a liquid, the 3 moles is going to have a higher entropy. Okay, so let's look at these. So we're going to predict whether the delta S is positive, meaning the entropy increases, or negative, meaning the entropy decreases. And remember, keep in mind, entropy measures the randomness, or how many microstates it can have. Okay, so number 1, we're going from water to water. So the moles isn't changing, the complexity of the molecule isn't changing. What is changing is the state of matter. So we're going from a flowing liquid to a crazy gas, which tells me that delta S is positive. The randomness is going to increase as we go from a liquid to a gas. Okay, so number 2, we've got AgCl to Ag ion plus chlorine ion to silver chloride as a solid. So first off, I look and I see, okay, I've got 2 aqueous things, and they are going to 1 solid. So the moles of substance is decreasing. I'm also going from aqueous dissolved in water to a solid. So this one, delta S, is negative. So my entropy is decreasing. Okay, let's look at this next one. Okay, so I have 4 moles of solid and 3 moles of gas. So I have 7 total moles, and 3 of them are gas. And in this side, I have 2 moles, and they're both solid. So I'm decreasing the number of moles. I'm getting rid of gas. That is going to dramatically decrease my entropy. So my entropy is going to be negative in this case. Next, I have N2 plus O2. So I've got 2 moles of gas, and I'm going to NO2, which is also 2 moles of gas. So now I have to look specifically at what are those. So on the product side, it's NO, it's one thing. And on the reactant side, it's N2 and O2, so it's 2 free moving things, which means that this side, the reactant side, is going to have more possibilities for microstates, which means that our delta S is negative. It's decreasing in this case as well. Okay, so again, you guys, it's all about comparison. So let's look at 2 comparisons. I want you to tell which one has the higher entropy and then explain. So stop the video for a second, try and answer these, and then come back to them. Okay, so hopefully you actually stopped the video. So we're going to look at this. So 1 mole of NaCl solid or 1 mole of HCl gas at 25 degrees Celsius. So the temperature is the same. There's 2 elements in each of those compounds. The complexity is the same. I have 1 mole of substance, so the amount of substance is the same. The difference that I have is that sodium chloride is a solid and hydrochloric acid, HCl, is a gas at this temperature. So our gas has more entropy, and that's because it's a gas. Okay, the next one says 1 mole of HCl gas or 1 mole of argon gas at 298 Kelvin. Okay, this one's tricky because I have 1 mole of each. They're both gases. They're at the same temperature. The only difference is that HCl is hydrogen and chlorine, and argon is just a single element, which means that the HCl is more complex. So HCl will have a higher entropy because it's more complex. Not very much, but it's going to have some of that translational energy, translational movement that the argon won't have since it's just a single molecule. Okay, so you guys are going to work on an entropy practice problems worksheet. It's a front and part of a back. You are going to analyze the equation and decide whether there's going to be an increase or decrease in entropy. And then give me a short explanation, just like we did here in these two problems, of why you chose that. What was your thinking? So that you can get immediate feedback, you are going to enter your answers in a Google form. So the form is linked in our question of the day slide on Moodle. So click on the link. It will have the equation and then the option of increase or decrease. And it'll give you an immediate, yes, this was correct. No, this was incorrect. If there are any answers after you see, or any questions after you see the correct answers, we can talk about it next time we see each other.